this at computer engineering. Probably there is someone else who can make a living out of knowledge of linear algebra, but for you it's really essential. Okay, so today we are going to build up on the knowledge that we covered in the last sessions. So if you remember, in the last sessions we were talking about how to solve a system of linear equations. And this system of linear equations, you know that it was an expression that looks like this. AX is equal to B, right? So this is what we have, and in this equation we gave A, we gave B, and we find X, or the question was to find X. And in order to do that, we were trying to go from A to reduced row echelon form of A, okay? So what was reduced row echelon form? It was a way to simplify all the information which is encoded in the data of a matrix. And what did we try to do? We tried to produce zeros, we tried to have leading ones, and we were using equations that looked like rho j star was equal to rho j minus lambda rho I. So this was an elementary row operation. So let's write it here. So these are called elementary row operation. So this is, let's call this one ERO. ERO. So these elementary row operations, we used to have also other operations that look like this. Rho I is we interchange it with rho j. This was another operation that we used, and we also did this C times Ri. So we can multiply any row with a constant C. So these were the elementary row operations. But now, today, we are going to approach to the problem slightly in a different way, and with this we mean the following. So far, we are trying to educate ourselves into understanding or conceptualizing that the matrices are linear transformers. Okay, so they are functions. You define a function to a matrix, and that's what it does. Okay, and when we talk about functions, they are linear functions, and I might expect it is good from all of us to keep this in mind. The first thing is to consider any matrix A like a function, and with this I mean the following. Assume we have a data x, and we apply a function f, and then we apply a function g, and then we apply a function h. Okay, and then this would be then equal to any capital H of x. Okay, so what do we mean from here? Let's give an example. We can have f of x is equal to x minus 2, g of x is equal to x squared, and h of x, this is equal to 7 minus x cubed. Okay, so, and then this is a linear transformation, this is another linear transformation, this is another linear transformation. How can you visualize this one? It would be the following. You can say that this f, this is equivalent to linear transformation matrix A. So let's put the matrix notation, okay? Or this other one, this corresponds to a linear transformation B, okay? It corresponds to a matrix. So let's use this language because this is the healthiest, the best possible visualization or the best possible interpretation that you could give, and it will help you more. So now, let's say, so what does ABC mean? What can we do with ABC? If you apply A to a vector and then B, this is equivalent to multiplying B with A, right? So what is, let's say, what is CAB? CAB, it's a cab, a taxi. That's what we call it, cab. But CAB is matrix C times A times B, and this is kind of equivalent to, if you apply this is a matrix, this is another matrix, this is another matrix, and we multiply those and we see what is B. B is G, A is F, okay, and C is H. And these are applied on this X, and let's see what we get. what is g of x? G of x is x squared. So we have here h of f of x squared. What is f of x? F of x, so let's find this. F of x is x minus 2. So we get here x squared minus 2. So this is h of x squared minus 2. What is h of x squared minus 2? This is equal to, who can help me here?
7 minus x squared minus 2 in the power of 3.
To the power 3.
Yes.
Okay, so now this in itself, this is equivalent or equal to an h.
Professor.
Yes.
Wait a minute, isn't x minus 2 all of it in power of 2? Not only x, because...
Let's check. You mean which? So what is g of x is x squared, and then f of x.
In this case, oh, it's f of x. Okay, okay.
Is good. Okay.
Okay.
Okay. So now here we have all of these functions that are operating on a vector x, and this would be, in principle, we are looking for this. Okay. So we can represent a series of certain operations as a single function. So then it looks like what is h of g of f? It's equal to 7 minus the cube of x squared minus 2. Okay, so this is the new operation. But how do we get these? We apply these linear transformations one by one. In the end, we just multiply this and we get the result. So it is good to always represent everything in here by matrices. How can we do it? This is what we are going to do next. So assume for a moment that we have a matrix which looks like this. Let's say A is equal to 1 minus 2, 3, 4 minus 3, 1, 5, 1 minus 1. Okay. So here we have some random numbers. And then we want to apply, so these are elementary row operations. Let's say that we want to apply the following operation. So let's say row 2 star is equal to row 2 row 2 star is equal to row 2 minus 3 row 1. Okay. So what will be the, if we apply this operation on this matrix, what we are going to get? The third row is not going to change, right? Because we did not apply any change in there. But what do we get for row 2? Who can help me here?
We get 3.
Yes.
We get 1.
1 or 3? Is it 3 or 1? Is this correct?
No.
What about the 3 there in the middle?
I think it's 1. Minus 3, minus 6. 1.
So minus 3 plus 6 is 3. Okay? And then we get 1 minus 9 is minus 8. Does it look good? Would you agree with this?
Yes, yes.
Thanks.
The first number of the row, it's 3 minus 3 times 1. 4 minus 3 times 1, so it's 1, not 3.
That's correct, yes. So this is 4 minus 3, yes, this is 1. We missed this, thank you. Okay. So this is what we get. So let's call this one, this is matrix A, and this is matrix B. So we did this operation, but then let's assume, let's check this statement. We are going to define elementary matrix. An elementary matrix, it's a matrix which we obtain from an identity matrix using elementary row operations. So let me ask you this, what is this statement? This is an elementary row operation. Then, what is an elementary matrix? It's 1, so let's define this new quantity. This is elementary matrix is one that we obtain from an I, which is n by n, which is identity matrix, and you apply elementary row operations. Okay, so this is the definition of an elementary matrix. So ERO is this, which is also this. Now, let's take the 1, 0, 0, 0, 1, 0, 0, 0, 1. Let's try to run this elementary row into here. So what are we going to get here? The first row, it does not change. Okay. The last row, it doesn't change either. So what about the second row?
We get -3.
Yes. What else?
1.
1, 0, right? Let this be the elementary matrix E1. Okay, let's write this one E1. And then let's apply E1 times A. What is E1 times A? This would be equal to 1, 0, 0 minus 3, 1, 0, 0, 0, 1. We multiply this with 1, minus 2, 3, 4, minus 3, 1, 5, 1, minus 1. This would be equal to, let's take out this B. Wait a second. Okay, no, I think we're good. Yes. So what do we get here? This is 1 times this, we get 1, minus 2, 3. And then we get here, let's multiply this row with the first column. We get minus 3 plus 4, we get 1. Then we have here 6 minus 3, we get 3. And here we get minus 9 plus 1 minus 8. And this stays, this is like this. This is 5, 1, minus 1. So if we look carefully, we observe that these two are equal. Okay, so it looks like applying this elementary row operation here and applying this E1, they are equivalent. So apparently we have defined, or we have determined a matrix which conducts this elementary row operation. Now, let's think about another elementary row operation, which would be the following. Let's think about this one in red. Row 2 star is equal to row 2 plus 3 row 1. Okay? So, let's see what, actually let's do it from here. So, let's derive this expression from the same identity matrix. This one will not change. This is 0, 0, 1. But then, what do we get here? We get 0 plus 3 times 1, right? This is 3, 1, 0. So let this one be E2. Okay? And then, let's find what is E2 times A. This would be equal to 1, 0, 0. 3, 1, 0, 0, 0, 1 times the same matrix so this is equal to the following. We get here 1, minus 2, 3, 5, 1, minus 1. And then here we have 3 plus, what is this? This is 3 plus 4, this is equal to 7. Wait a second, 4 into times A. Okay, so we get 7 here. But actually, let me think for a moment. Why don't, actually, let's apply on this one, let's do E2 times B. Where, let's not forget, I forgot on this one, let's multiply this one with the matrix B, not the A. For the moment, applying E2 on A, we'll just find another matrix. So, allow me to change this one, we'll change just this row. B is 1, 3 minus 8. So it looks like only the second row is changing regularly. So then here we'll have 3 plus 1, this would be 4, minus 6 plus 3, minus 3, and then we have 9 minus 8, we get 1. So we see that this is matrix A. So what do we have in this row here? In this row, we've got the E1A was equal to what? We got B, right? Because this was B, this is also B. And then in this row, what we did E2 times B. What did we get? We got A. But then, what is B? We say E2 times, instead of B, let's write E1 times A. Okay? And then, we know that when we multiply 3 matrices, we can multiply the first 2 and then with the third, or we can multiply the second and the third and then with the first. So here, we can change the parentheses and we can write the following. We can say E2 times E1 times A, this is equal to A. So, if we see this expression, what can we say here? Any comment? If this is this product times A equal to A, this means that this is an identity matrix, okay? Because identity matrix times a matrix A would then be equal to A. So in this case, we could say that E2 inverse is equal to E1. So these two matrices, they are inverses of each other. You can try this as an exercise. You multiply E1 with E2, okay, this one with this one, and most probably you're going to get an identity matrix. So from here, we can see that these two linear elementary row operations that are reported here, they are inverses of each other. So if we modify the matrix A with this row, if we apply this row back again, we go back to the original A, okay? Because this is equivalent to having the following. So let's assume that we have the matrix, sorry, the matrix A, yes, that was correct. We have the matrix A, then we apply the matrix E1, okay? And then we apply the matrix E2. But these are inverses of each other. So this is equal to identity matrix times A. So from here, it looks like we can define that these elementary row operations are expressions or matrices which we obtain from the identity matrix, and this is how we use them. Now, one other thing that we can add here, which is very important, which you can write this down. So we talk about elementary row operation, we talk about elementary matrices, and now we want to add a new definition, which we mentioned here for the first time, is that we can say that A and B are row equivalent. So A and B, they are row equivalent because B is found from A by applying with an elementary matrix. So elementary matrix, let's call this E. If B is equal to E times A, then this implies that A and B are row equivalent. Okay, so this is something new that we see. Now, from here, it looks like, do you have any questions so far? So we're saying, do you have any questions so far? If you're saying, since you are saying nothing, that means that you have questions, okay? Probably we should ask it like this. Don't you have any questions so far? You say yes. By just being silent or by just keeping silence. Now, let's see. So far, we're looking into these definitions that are on the board, and then we look at a different problem, which we can pose it like this. Assume that we have a matrix A, which is 1, 2, 4, 1, 3, 6, minus 1, 0, 1, minus 1, 0, 1. Let's say that we want to determine the inverse of this matrix. But how can we do this? From the previous sessions in this class, let's not forget that we started from A, we applied elementary row operation, ERO, and we found the reduced row echelon form. Okay, this is what we did in the previous sessions. Now, what we are going to try here is, let's start with matrix A, and also a small reminder, when we did the solution of systems of linear equations from this equation AX equal to B, we used to have a matrix that we called what? Do you remember what did we call that matrix? Can you read this?
Augmented matrix.
Yes, okay, so augmented matrix, which we constructed like this. We put A and we merge the B, okay? Can we do this merging? Yes, we can, because the number of rows in A is equal to the number of rows in B. So if this is A3 by 3, we cannot merge a matrix that is going to look like this, 2, 3. We cannot have this kind of merging, because the matrix cannot be like with matrices are rectangular, okay? So you're going to see this in the future years when you go to the second or the third year. Often, when you are dealing with matrices, you always you either concatenate them or you merge them in the same way like we do here. And sometimes you should be careful, because you have to always check if you are writing a program. You might have to check what is the size of your matrix. You want to concatenate them, but it will not work. So just go over this. Be careful on this aspect. So now, instead of merging the B, let's assume that we have this other equation. AX is equal to the identity matrix, okay? So, kjo B-ja nuk është gjithmonë vektor. Kjo B-ja mund të jetë matricë 3x3, okay? B-ja, po them pra këtë B, mund të zëvendëson dhe matricë 3x3. Dhe kjo është, ne mund ta shkruajmë të relacion A e X bazë me identity matrix. Dhe kur mundohemi ta zgjidhim, do bëjmë të njëjtën mënyrë. Këtu bëshim AB, këtu tani ne do të shkruajmë AI, which is the identity matrix. D'accord? Dhe pastaj, and then we try to reduce the entries in this matrix A. So let's try to do the same here. So we wrote the A, so this is A. Let's write the identity matrix, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. And let's apply the reducer, the ERO. Let's apply the elementary row operations, which are defined here. What would be the first elementary row operation here? So let's assume we want to make these zeros. Let's not forget our initial objective is to produce zeros. How can we make this 0? We can say that row 2 star is equal to what? Row 2, then what?
Minus row 1.
Thanks, minus row 1. What about row 3 star?
Row 3 plus row 1.
Plus row 1, that's correct. Okay, so let's write then the answer here. I think you can see this part on the board. Do you see the board clearly? Can you comment on this? Aduga Drasa?
No.
Okay. So let's continue here. The first row is not changed because this is the pivot row 1, 2, 4. This is 1, 0, 0. And then here we subtract these two. 1 minus 1 it's 0. 3 minus 2 it's 1. 6 minus 4 is 2. 0 minus 1 minus 1 1 0. Then we add these two. We add pair element-wise pairing. So this is 0, 2, 5, 1, 0, 1. Okay. Then we made zeros here. The next step is to make this 0. How can we make this 0? We can say that row 3 star is equal to row 3, then what?
Minus 2 row 2.
That's correct, because this is the pivot now. Don't forget this. So now this is the pivot, and then we move ahead. This is 1, 2, 4, 1, 0, 0, 0, 1, 2, minus 1, 1, 0, and row 3 is equal to row 3 minus 2, row 2. So here we have, this is 0, 2 minus 2, 0, 5 minus 4, 1. 1 plus 2, 3, 0 minus 2, minus 2, and then 1 minus 0, this is 1. Okay, so what is the next step that we need to do? We got done here, so we did this part. So these zeros, we got them, we are good. And then we move to we want to make zeros above the diagonal. So this is what we should do next. And how can we do this? This will be row 2 star is equal to what?
Minus 2 row 3.
That's correct, minus 2 row 3. Why do we do this? Because
it's below.
This one, that's correct. This one has to make a 0 here and here. What about row 1 star? What is row 1 star? Probably we could do this, and then we move ahead, and we get the following. The third row does not change. 0, 0, 1, 3, minus 2, 1. And then we have here 0 minus 0, 0, 1 minus, this is 1, 0, and then here we get minus 1, minus 6, minus 7, 1, plus 4, 5, 0, minus 2, minus 2. Then the first row, it's this is 1, this will not change. 4 minus 4, 0. And then we get here 1 minus 12 minus 11, 0 plus 8, 8, 0 minus 4, minus 4. The next step which remains is the following. We have one final non-zero term. We need to make 0 this 2. To do this, we could get the following. We say row 1 star is equal to row 1 minus 2 row 2. Okay? So, finally we get 1, 0, 0, 0, 0, 1. And these are not changing. 3 minus 2, 1. Minus 7, 5, minus 2. And then we get the following. So we have minus 11 plus 14. What is it? I get the 3. 8 minus 10 is minus 2. And then we get minus 4 plus 4, 0. Okay, so what is this? We started here with A, okay, and this was I, and now we get here reduced row echelon form of A. This is what we are, what our objective is. We get here I, and this one here. What is this new matrix here? How can we call this one?
It's the inverse of matrix A.
Yes. How can we say that? Are you sure that this is the inverse of matrix A?
It should be, because we wrote that AX is equal to an identity matrix, meaning that they should be inverses.
Okay.
To produce an identity matrix, they should be inverses.
That's correct. Okay. So now let's have a look here. We started with this, right? And then we applied many operations here. So how many operations did we conduct? So this is the first reduced row, sorry, this is the first elementary row operation, which would correspond to E1, right? Like an elementary matrix E1. Then this would correspond to an elementary matrix E2. This would be E3, okay? So for all of these, we can construct all these little matrices. E3, this would be E4. It's better if I use a different color. So here I have it. This would be E5. And this is our E6. And finally, we get the following. So now, how can we write down the overall operator here? So I think we started with E1, okay, then E2, then E3, E4, E5, and E6. So we apply this first, this. But then what we can do is that the product of all of these matrices that are shown here, so we can say that E6 times E5 times E4 times E3 times E2 times E1 is going to be equal to, we can write this one as elementary matrix E, okay, so wat maar een product in het zitturen, een beetje. So we get this E times AI. And then the way that we've done these, I believe we can take this E inside the parentheses. Would you agree with this? Because we have applied this function on this and on this simultaneously. So we can write here, this is equal to EA times EI. Okay? Now, what is this equal to then? EA, what was E times A? It's the identity matrix. This is what we got, right? So after we applied all of these functions, here we got the identity matrix I. And what is E times I? E times I, kur shumëzoni matricën me identity matrix, është në shumë, okay? So what is E times I? It's E. But then we also observe one thing here. So E times A is equal to I. Okay, if we look just at this relationship, this implies that so from this equality, which we have shown it here, from this equality, we can conclude that E is equal to A inverse, because we know that A inverse times A, this is the only possible combination such that we can get an I inverse. Okay, so it is true, you are correct, this is the A inverse. So it looks like we could determine, we could find what is the inverse of a matrix using elementary row operation in the same way that we have applied them when we try to find the solution of the system AX is equal to B. Okay, so, but now we have also a different way how to find the, So I'm erasing this. Do we have any question for this far?
Professor, what happens if A isn't a square matrix, let's say?
Then you cannot find the inverse.
Yeah, but if we can we like write the augmented matrix of A and I then?
Yes, you can. Yes, you can. But the same way that we used to write, yeah, that's a good question. So you are saying the following. You can have a matrix which looks like this. 1 minus 3, 4, minus 2, 1 minus 1, 2 minus 2, 3, 7, minus 5, 8. So this is a matrix which is, actually, let's think about this one. Let's work it out together. Thank you for the question. But let's see what could happen. So we have a matrix, and you are asking whether we can augment this one with identity matrix, right?
Yes.
I don't know. Let's see. We can conclude into something, but I have not memorized. I don't know. Let's see all together what we could get. So if we augment it like this, what does this mean for us? I believe I can erase this part. So you have to answer this question, okay? You ask the question, but let's work it out together. So we see from here that we have a matrix A. What is the dimension of A?
3 times 4.
That's correct, 3 by 4. And then, in principle, we have to multiply this one with some other matrix. Let's call it matrix B. Let's call this matrix B. We don't know the dimension, but the answer is going to be equal to the identity matrix, right? Traditionally, this is 3 by 3. Traditionally, we write AX is equal to B, little b, but let's have this one. Now, what do we see from here? What should be the dimension of B?
4 by 3.
That's correct, 4 by 3. So apparently, this B is not a vector anymore. So allow me just to write this one in a second. So far, we have often seen expressions like this. A, which could be 3 by 4, times a vector, which is 4 by 1. This would be equal to a vector B. AX is equal to B. This is how we traditionally write. This would be 3 by 1. Okay. So this one, we've seen this so often, we are comfortable with this. But then, if we have this situation, you're asking whether we can do it. Yes, we can. And but if we merge, not merge, if we let me think for a moment. If we start with this matrix, you know what? Why don't you do this as a homework, okay? So I'm gonna, because I want to see you work this out, and you find this on yourself. What is B? Okay. And let me think also something for a moment.
Professor, just sorry to interrupt. Just to clear something up, identity matrices must be square matrices, right?
Yes, of course, yes.
Okay, thank you.
Yeah, you're welcome. Identity matrix, there should be square matrices because they have all elements are 0, only the diagonal they are equal to 1. So, so please solve this problem. Okay, this is your for the section of the electronics engineering. This is a homework. Okay, you have to submit this one in Google Classroom. You have the knowledge how to solve this one. Just try to obtain the reduced row echelon form out of the A and rewrite the equations. Only that in this case, the B, the unknown vector, well, you know it from here actually. So the first one, this is x1, this is x2, this is x3, and this is x4. Okay, so this is x4, yeah. But let me think for a moment. Yeah. Okay, that's correct. And you move ahead. Try to solve this one. Now, this was we did the elementary row operations.
Professor?
Yes.
What about E, the elementary matrix? Does it represent only operations between rows, or even division in a single row?
This is a very good question.
Yeah, I also had a similar question to make. Like, how do you get the matrix E from all of the operations?
Shall we do a couple here?
Okay, if everybody agrees.
Yes, yes. Okay. For example, let's see here. What is E1? Let's see what is E1. E1, it corresponds to this elementary operation. Okay, let's have a look here. But we did not answer the first question. The first question was this. Can we have an elementary row operation which is equal to a constant times a row? This question still stands. Let's keep it for but the answer to this is yes. We can, as we are doing these operations, we can, what's the name? We can divide one row with a constant number, and we're going to see examples for this. So that's the answer to the first question. The second question, let's see what is E1. E1, we start from 1, 0, 0, 0, 1, 0, 0, 0, 1. And then what is the elementary row operation? Row 2 minus row 1, okay? So this means that from here, this would be, and notice, only row 2 is going to change, right? This is a row start. So this stays the same, 0, 0, 1. Would you agree here? And then we want to get the row 2. Row 2, it's 0 minus 1. This is minus 1, 1, 0. So this is E1, okay? So we found E1. What is E2? So let's try to get E2 from here. What is E2? This is row 3 plus row 1. So we just add row 3 with row 1. And again, the first two rows, they don't change. Are you following here?
So you name the matrix E1 after you make the row operation on it.
Yes, yes.
Okay.
So
okay.
Identity matrix 3 by 3. And then we apply this elementary operation, we get this. That's true. So what should we get here? Row 1 plus row 3. Okay, can you do this? So I'm asking, if we apply this elementary row operation on this identity matrix, what do we get?
1, 0, 1.
Yes, 1, 0, 1. Here we have E2. Then, what is E3? So let's have a look at this one. What is E3? What did we change in E3? Apparently, we changed row 3, right? If we change row 3, then the first two rows, they don't change. So we have row 3 minus 2 row 2. So what is this then?
Minus 1, 0, and
you said minus 1? Row
1,
3
0, 1.
Say it again.
Oh, so we should transform this from the identity, from the identity matrix, from the first one.
Yes, it's for the identity. So I say from here we go here.
Oh, okay, okay. It's minus 2, 0.
Does this look correct? Because we have row 3 minus 2 row 2.
No, it's minus 2, 0, 1.
But it's minus 2 row 2. Row 2 is a pivot. Okay? So this operation here, which I'm putting this in red color, this is row 3, which is this, minus 2 times this. Okay? 0 minus 0, 0. 0 minus 2 is minus 2. 1 minus 0 is 2. Is 1. Is it clear? So I'd like to confirm if this is clear. So let's check. This is row 3 star is equal to row 3 minus 2 row 2. We are talking about this one, right? And then this is equivalent to, what is row 3? Row 3 is 0, 0, 1, right? And then minus 2 row 2. What is 2 row 2? Is it 0, 2, 0? Would you agree here? Yes or no?
Yes, it's clear, but my internet connection is very bad at the moment.
Okay, don't worry. But okay, so it looks like this is our E3. So this is how we can derive all the possible elementary matrices E1, E2, E3, E4, E5 up to E6. So we are good here. Any further question?
No, it's clear.
Okay, thanks. So we talked about the elementary matrices, row equivalents, and now we're going to talk about the following. If any matrix A is a square matrix, how do we report a square matrix? We say if A is n by n, this is a square matrix, then below statements are equivalent. So what are the statements that are equivalent? The first statement is the following: A inverse exists. So A inverse exists is the first statement. If this is true, what are the statements can we see as an equivalent one? 2. AX is equal to B has unique solution. Now, if a system of equations does not have a solution, CHUM method, how do we call it?
Inconsistent.
Inconsistent, that's true. But if we have a solution, we call it consistent. So it looks like if ce o să matrița A e ca inversion, se inversion nu că există un the inverse doesn't always exist. But if it exists, apparently this equation, it is consistent and it has a unique solution. How many possible solutions can a system have? It's 0, no solution at all. It's 1, or infinite number of solutions. So apparently this has a unique solution. This is pretty much a very good option because we have a single point. We don't have an infinite number of solutions like that are represented by a line, or we don't have an infinite number of solutions that could be represented by a plane. So this is what we get. The third statement, which is equivalent to the first two, is the following. If we have AX is equal to 0, this has only the trivial solution. What do we understand from the trivial solution?
It's that the solution is 0.
That's true. So trivial solution, why is it 0? Let's see for a moment. 3x is equal to 0. What is x?
X is 0.
X is 0 here, that's true. Now, for a system of linear equations, where this is a matrix, solution in this case, it could even be a linear combination of non-zero numbers in here. But in this case, if the inverse of A exists, then we have only the trivial solution, which means that x is equal to the zero vector, okay? The fourth statement, which is equivalent to the first three, is the following. The reduced row echelon form of A, is equal to what? Can you find it? That's true, yes. So if we try to find the reduced row echelon form using elementary row operations from a matrix A, then this would be equal to the identity matrix, and I think this is what we have seen so far. So these were equivalent statements. Now, I think we found what the inverse matrix was using elementary row operations. And then we're going to determine, actually maybe we need this space, so let's make use of this. Next, we're going to talk about the determinant, okay? Determinant, it's a number which can be associated to a matrix, and it carries very important properties. It is amazing how impressive is this number, because it is equivalent to the volume. It is equivalent to the volume in 3-dimensional space. It is equivalent to the volume in 5-dimensional space. It is equivalent to the volume in 2-dimensional space, which probably can be called the area. But so assume for a moment, what do we mean with a volume in 5-dimensional space? Well, if you have a matrix which is 5 by 5, you can calculate the determinant, and then if it is a large number, that means that you are occupying a lot of volume in 5D, which we cannot perceive. But you can perceive what is the dimension in 3D. But now, let's see the determinant, and let's start the definition of the determinant from the simplest case. Let's assume the matrix A is a 2 by 2 matrix, and this is equal to A, B, C, and D. So determinant in this case, and by the way, in the first week, when we first talked about the inverse matrices, we said something which you're not supposed to memorize it. Some smart students do memorize that, but it's not always advisable. We said that there is a formula for A inverse, which would be 1 over AD minus BC, and here we get DA minus B minus C. Okay, so this is the inverse of A. This important quantity here, this is called the determinant of a 2 by 2 matrix. Okay, so if we divide by 0, what does this mean?
That it's undefined.
The matrix doesn't have an inverse.
That the inverse doesn't exist.
Doesn't exist, that's correct. So this doesn't exist. So A inverse does not exist. So you can make a relationship with this theorem. Actually, this is a theorem which we stated here. So apparently, A inverse does not exist. So, but what if it exists? If it exists, this is a new information. You can write it down, or you can conclude. So this means that the determinant of this matrix A is different from 0. Okay. So to these relationships, or to the intuitive approach of how you think about matrices and properties of matrices, you can add this here. So if A inverse exists, the determinant of A is different from 0. This was the determinant for a 2 by 2 matrix, which is equal to the product of these two numbers, okay, minus the product of these two numbers. Okay, so we crisscross them around. Now this is the determinant for a 2 by 2 matrix. If we have a larger matrix, what we do is that we use the property of the determinant of a 2 by 2 matrix in an intuitive and in a smart way. Let's give an example. Let's assume that we have, let's have a matrix which is 1, 2, minus 3, 1, minus 1, 2, 5, minus 4, 1. So here we have a 3 by 3 matrix, and then before we go any further, we are going to define a quantity, which is sometimes not a quantity, it's just an index, okay, or like an operator. Let's call it an operator. So we have an operator which we can denote it like this. Minus 1 to the power I plus j. Okay? This is the operator. And let's think, for example, cât duży tu? Ce adresă ca cât duży? Cât tu?
2, 3.
8, 2, 3.
This is it, okay? 8, 2, 3. Now, this 2 here which is denoted as the number in the second row and the third column. This can be associated with a number like this, -1 to the power 2 plus 3. What is this equal to?
-1.
-1, thanks. What about, what is this 5? What is the address of this 5 here?
It's 1 because it's 3, 1. 3 plus 1.
3. So this can be associated with an index -1 to the power 3 plus 1. What is this?
It's 4. So
-1 to the power 4?
So just 1.
It's just 1, that's correct. Now, this is, so for any number that we can find in a matrix, you sum up the, what's the name, the indices that you, to find the location, and you use this as a power to the number -1. So in this case, if we use this notation here, you can always think that you have a relationship which goes like this. Sorry, it's a plus, minus, plus. So you can prove this one, but it looks like each time you move left, right, you change the sign. So A11, what is, if you are talking about this one here, the very first one, what coefficient does this have?
yeah, because it's 1, 1.
-1 to the power 1 plus 1, that's correct. -1 to the power 2, that's good, 1. Keep this in mind, and now let's find the determinant of a 3 by 3 matrix. How can we do this one? The first way, we can expand, you can use this keyword, okay? You can expand along row 1. What do we mean here? We mean the following. We say 1 times the determinant of the matrix which is constructed after we remove the first row and the first column. What do we get from matrix A if we remove from here the first row and the first column?
You get matrix -1, 2, -4, and 1.
Thank you. And then, so we're expanding along the row 1. What is row 1? Let's write it here. It's 1, 2, -3, okay? So then we get the other index 2, but we do here -2. Why do we do -2? Because this 2, it has this minus sign here, okay? So we do here -2 times what? The 2, it is first row, second column. So what remains from the matrix A if we remove the row of this number 2 and the column of this number 2? So what should I write here?
1,
1, 2, 5, 1.
1, 2, 5, 1. Then we go to the next element of the row of the first row, -3 times. Let's remove the row of -3 and the column of -3. What remains?
1 -1, 5.
-4. Thanks. So what is the determinant of this little matrix? -1 plus 6 plus 8, 7. This is 1 minus 10 minus 9, -4 plus 5, 1. So then the determinant here is equal to 7 plus 18, 25, -3, 22. Okay? So this is the determinant of this matrix. So it looks like if we have a matrix like this, the first vector 1, 1, 5, it defines a point in 3-dimensional space. So let's think about like this. So we have here x. Of course, I cannot perfectly draw this one on a board, but if we have x, y, z, the first row is 1, 1, 5. What is 1, 1, 5? 1 unit here, 1 unit here, and 1, 2, 3, 4, 5. We get here. So we get a vector which we can find it like this. So we get a point, okay? This is this point in 3-dimensional space. Then we have 2 minus 1 minus 4. 2, we move -1, and we move this way, and we're 4 units down. 1, 2, 3, 4. We get this other point, okay? The first one was here. The other point is -3 to 1, -3 to 1, -1, -2, -3, 2, 1. So we got this point. Okay, we move x, y, z. So we get this point, and this vector. Now these three vectors, they are the size of a three-dimensional structure whose volume is 22 units cube. Okay, good. So this was finding the determinant expanding along row 1. Let's find the determinant expanding over, you pick one row or one column of your choice.
Sorry, Professor. So you said that the determinant represents the volume, but
yes.
The vectors, what do they represent geometrically? Do they represent the vertices of the shape which is formed, or?
Exactly, yes. So
the vertices, so, okay.
Yeah.
Okay, thanks.
You're welcome. So this is what would go. So if we try to do the best we could, you could draw here a parallelogram that goes like this. So you have this, this, and this. And then you move into the third dimension by moving this way, okay? This way, this way. So you join these, and you fill it with water, and you have 22 meter cube if the unit size is 22, okay? So this is the volume. Now, let's expand along, can you pick one row or one column here in this matrix?
Can we pick a column?
Yes, you can.
Okay, the second.
Second column, okay, 2 minus 1 minus 4. 2 minus 1 minus 4. Okay, so here we have a column. And then we have to find the determinant. So then the determinant is equal to, first we start with 2. What is the index of 2? We write here minus 2 times. Do we understand why we say minus 2?
Yes.
Yes, because this minus 2 has this negative number here. So this is minus 2 times what remains from matrix A if we remove the, where is this, if we remove the row of 2 and the column of 2.
1, 2, 5, 1.
1, 2, 5, 1. And then we have minus 1, minus, what remains if we remove the row of minus 1 and the column of minus 1?
1 minus 3, 5, 1.
Yes, okay. And then we have minus 4. What should I write?
4.
Plus 4, that's correct. Times 1 minus 3, 1, 2. Okay, so what is this little determinant here? This is 1 times, this is 1 minus 10 minus 9, 1 plus 15, this is 16, and 2 plus 3, 5, okay? So then here we have 18 minus 16 plus 20. So we get here 22. Okay, we got the same determinant.
When plus 16, it's 5 times minus 3, and minus, it means it's plus 16.
Are you asking about this one?
No, the middle one.
Here, this is
Minus 3 times 5 is minus 15.
yes.
And the minus before it, from the minus one, it's minus, so it should be plus.
Yes, I think we did this. Wait a second. Yeah, this is plus 16, but there is this minus here.
But it's 5 minus 3.
No, but this is 1 times 1, this is 1. Minus 15, this is 1 plus 15, right? Because the determinant of this one, it's 1 times minus 3. Sorry, that's a mistake. 1 times 1 minus 5 times minus 3. So this is equal to 1 plus 15. This is equal to 16. Is it clear? Because the determinant is A times D minus B times C. Pra përdorën skajet e kundërta të katrorit. Kulmet e kundërta. Is it clear now?
Just a minus, I don't get why it's not plus and it's minus.
Okay, but are we okay so far? This is -2, -1, and then what is the determinant of this 2 by 2 matrix? It is, let's see here, the determinant is AD minus BC. So it's this number times this, 1 times 1, that's 1, minus 5 times -3, okay?
It's -5 times 9.
Is it? Okay, so we got here 16, we got 22, and this 22 is the same number with this 22 here. So actually, when you think about this one, it is an interesting way to define the problem this way, for sure. But you could say that when you try to find the determinant, this is, you are trying to get a 22 out of how many different combinations? 1, 2, 3, 6 combinations. So you can find 6 different combinations that you add and multiply numbers to get the same determinant. Okay, so this was the determinant, and then once we have the knowledge of the determinant, we have the background to approach to a problem slightly different. Let me think for a moment. I think we can pick up this matrix, and 1, 2, 3, -1. Okay, we randomly selected these numbers, but let's. The next question, or the next thing that we're going to go over, is how to find the inverse of a matrix. To obtain the inverse of a matrix, we have a procedure that follows like this. Any matrix which is n by n, sorry. From this matrix here, we can define a matrix M, okay, which is called the minor. And from the minor, we can define an element Cij, which is equal to -1 to the power I plus j times Mij, okay? So let's say we had a matrix A, we define a matrix of the minors, then all the elements of the minors, they're multiplied by -1 to this term, and we get the cofactor. So this is the minor. This is called the cofactor. Okay, and then we find the adjoint. We say that the adjoint of A, this is equal to the transpose of matrix C. Okay, and then from the adjoint, we can define that the inverse of A, this is 1 over the determinant of A times the adjoint of A. Okay, so we have a procedure that looks like this, which we can follow step by step in having 1, 2, 3, 4, and we find the inverse. Let's do this one by solving an example. What we don't know so far is only this, okay, the minors. What is the definition of a minor? Once we know that, everything, it seems relatively simpler. So the key is getting these numbers. Now, the definition of a minor is the following. So minor is a matrix which carries the determinants, okay? Determinants after removing or cancelling out ith row and jth row.
Sorry, can you say that again? I didn't get the part of it.
Say it again.
Can you say that again? I didn't get the part.
Sure. We're trying, what we don't know so far is that for the first time we are hearing the word of the minor. What is the minor? It's a matrix which is composed of determinants of the matrix that remains after removing ith row and jth column. Now, think about the 3 by 3 matrix, okay? You pick the first element, A11. You remove the first row and the first column, find the determinant. This is what we're talking about. But let's do this through an example, okay? Let's pick a matrix, and let's assume we have the matrix A, which is equal to 1, 2, 3, 4, 1, 1, minus 1, 3, 0. Okay, so the first question is, we want to find the minor matrix, M. What is M? So, let's see, M11 is equal to the determinant of the matrix which remains after we remove the first row and the first column. So the determinant is 1, 1, 3, 0. So what is this? Would you agree? M22. What is M22? We remove the second row and the second column, and we have 1, 3, minus 1, 0. What is the determinant here?
Three.
3. What is M12? We remove the first row and the second column. What are we left with? 4 minus 1, 1, 0. So what is this?
1.
Okay, that's 1. So let's write these numbers here. So this is a cofactor, but I need space, cofactor. So M is equal to minus 3. Then 1, 2, this is 1. M2, 2, this is 3. So we have to identify this. So can somebody find the cofactor, sorry, the minor element for this 0? What is it?
Minus 7.
Minus 7.
Minus 7, let's see. Minus 7, let's go. Minus 7. What about here for this 4?
Minus 9.
That's correct. What about this minus 1?
Minus 2.
Minus 2.
Minus 1. Minus 1.
Minus 1, okay. Minus 1. And then let's do the rest. This is 1 minus 12 minus 11. I might do some mistakes. You can always correct me. But this is 12 plus 1, 13. And here we get 3 plus 2, 5. Okay. This is, so we found it. What is the rest? The rest, we just multiply with this minus number. This is plus, minus, plus, minus, plus, minus, plus, minus, plus. Okay? I think we didn't do any mistakes. So here we define the cofactor matrix, which is going to be the following. So it looks like we are going to change the signs here, 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 sorry, and here. Because these are the only minus ones, okay? So this is going to be minus 3, minus 1, 13, 9, 3, 5, 11, minus 1, minus 7. Okay, so we found the cofactor matrix. The next step is to find the adjoint. Adjoint, so which we spell it like this. We spell it like adjoint. Yes.
Minus 5.
Let's check. Yes, it's minus 5. So this one changes sign. Thank you. So then the adjoint is equal to the transpose of C. Now, if it is a square matrix, the transpose is easy because we take the mirror reflection with respect to the diagonal. So in the transpose, diagonal terms don't change. So you can do it like this. Minus 3, 3, minus 7, okay? And then you can take the reflective. This minus 1, you write instead of the 9, minus 1, this is 9. Or you can think it also like this. The first row becomes the first column here. So we get minus 3, minus 1, 13, 9, 3, minus 5, and the third row becomes a column minus 1, 11, minus 7. Okay? And then, so we found the adjoint. The next step is to find the inverse. So, well, to find the inverse, we need to know the determinant. What is the determinant of matrix A? Let's try to identify it. And we have here M11, M12. So if we expand along the first row, which is 1, 2, 3, we're going to get this determinant. 1 times 3, so this is 3, minus 2 times M12, 2 times 1, plus 3 times, this is, actually we have all of these numbers we have them here. Minus plus 3 times, so 3 minus 2, 3, 13, yes. So in fact, the determinant here, you can easily see, that's interesting actually, I never thought about this one this way, but to find the determinant, if you expand it along the first row, you're going to look at these products, okay? That's impressive. So this is 1, so plus 1 times minus 3. Oh, it's minus 3 then? Wait a second. Yes, it is minus 3. So we made a mistake here. This is minus 3. Then we have minus 2 times 1, and plus 3 times 13. Okay. Then, if we want to expand this one along the second column, we take this, this, and these numbers. Okay. But can you find what is the determinant here? This is minus 3, minus 2, plus 39. This is equal to 34. So if this is 34, then we say that A inverse is equal to 1 over 34 times minus 3, 9, minus 1, minus 1, 3, 11, 13, minus 5, minus 7. Okay? So we found what is the matrix, the inverse A. Now, here we observe something interesting, is that I can ask you the following. Саш елементи А ніж. Саш А ніж.
Minus 3 per meter second.
That's true. So it's something like 0.09 or 0.08. Okay, so it's like minus 3 over 34. This is something less than 0.1. It's less than 0.1. Probably it's equal to around 0.09 or who knows. Okay, something around that number. So what about the other number, the 9 divided by 34? This is like around 10 divided by 30. So this is 1/3. So this is around 0.33, but it's smaller, 0.30 probably. Okay, good. So it looks like we don't have integer numbers. What would be a case when you have a matrix A, like this one here, and the matrix A inverse has all the entries being integer numbers? When could this be possible? When? I mean, probably if determinant is 1, right? If determinant is equal to 1, because we see that we are dividing all of these adjoint numbers, we're dividing them by the determinant, okay? Imagine for a moment that the determinant is 5 or 7. 7 is a prime number. Is it possible? I mean, it could be, but think about this one. Imagine you have a matrix A, determinant is 7, and then you come here. Could it be possible that all of the entries here, there are multiples of 7? Pra që plot pjesohen me 7, dhe ku pjesohen me determinanti që është 7, rezultatet do dalin gjithë më të plot. A ndodh shpesh kjo? It's a very small probability, right? Very small possibility. But if the determinant is plus minus 1, so in case the determinant of A, so we denote the determinant of A like this. Determinant of A is also defined like this. So if you see the absolute value looking like structure around the matrix, this is called the determinant. If this is plus minus 1, this constitutes a family of matrices which are called unimodular. Unimodular matrices. And unimodular matrices are very important in mathematics. And you, as electronics engineering, you might keep this in mind, or you can take down a note saying that these unimodular matrices, they have their equivalents when you do some transformations in electronics, which you will be forced to do them in the second year or in the third year when you deal with electromagnetic waves or electromagnetic field theory. They are impressive, they are very good, they are very interesting properties which carry some equivalent properties. I'm not saying that they are exactly the same, but at least they are equivalent in the way that we work with them. Okay, so now we learned how to find the inverse of a matrix using the cofactors and the minors. The other technique, it was when we used the elementary law operations, starting from A and trying to determine the reduced row echelon form of a matrix A. So we did this example. What is next? So we covered the... And what would the determinant be useful for? Well, we have a very interesting relationship. And one final thing. Do you have any question for what's on the board? Is it all clear?
Yes, it's clear.
Okay. Now, determinants, we can use them to solve systems of linear equations. And what we're going to see next is that it's a rule which is called Cramer's rule. There used to be a very beautiful movie, a very old one, which was Kramer against Kramer. It's a classic, but this is something different. So for any system of linear equations, AX is equal to B, the values, the xi is equal to the ratio of the determinant of AI divided by the determinant of matrix A. So this is the Cramer's rule. That's it, but how we can formulate this one? The matrix AI is a modified matrix where the B is inserted. We can remove one column from matrix A, we substitute it with B, and then we find the determinant, and then we divide with the determinant of A. So let's write it like this: determinant of AI star divided by the determinant of A. They are the same thing, but this is what Cramer's rule is about. Now, we can understand this one always doing an example. And let's see one. So let's assume we have x plus 2y plus 3z, this is equal to 7, minus x plus 2y plus z, this is equal to minus 3. Then we get 4x plus y plus z, this is equal to 5. So here we have the system of linear equations, and then the next thing that we need to do is we need to determine the coefficient matrix A, which is 1, 2, 3, minus 1, 2, 1, 4, 1, 1. This is the coefficient matrix. And now, in this coefficient matrix, we know that the first column, it corresponds to which variable? Coloana para scuti perché?
X.
That's true, because we look at these, we have the x is 1 minus 1, 4. This is where it is, right? 2, 2, 1 is y. So here we can say that this is the x variable, this is the y, and this is the z. So now, with these, we can, so this is a, but then we can determine, or we can define ax, which is equal to the, and let's not forget, the vector b is equal to what? It's 7
minus
3.
5.
Yeah. What is AX? Let's substitute the column of X with the answer vector, which is 7 minus 3, 5, 2, 2, 1, 3, 1, 1. This is AX. Then the AY is going to be the following. We get 1 minus 1, 4, 7 minus 3, 5, and then we get 3, 1, 1. The AZ, this would be 1 minus 1, 4, 2, 2, 1, and 7 minus 3, 5. So from here, the first thing we need to determine is the following. What is the determinant of AX? Then, what is the determinant of AY? And then the determinant of AZ. So what are these? Let's try to determine these. So let's do the first one. The first one is 7 times 2 minus 1, 1, minus 2 times minus 3 minus 5 minus 8, plus 3 times minus 3 minus 7 minus 13. Wait a second, no. Minus 3 minus 13, yes. So this would be equal to 7 plus, what is this? 16 minus 39. This is 23, 16. Okay, so this is equal to 16. So it looks like this is 16. AY and AZ, we need to determine these. But meanwhile, we need also what is the determinant of A itself. So this is A, right? So let's write here what is the determinant of A. Determinant of A is going to be 1 times 2 minus 1 is 1, minus 2 times minus 1 minus 4 minus 5, plus 3 times minus 1 minus 8 minus 9, minus 1 minus 8 minus 9, and we get minus 27. Minus 27 plus 1 minus 26, 16. So this is equal to 16. Okay. Then let's find the AY. The determinant of AY, it is 48. We can calculate it. And the determinant of AZ is minus 64. Okay, and what the Cramer's rule states, it states the following. It says that x, the variable x, is equal to determinant of ax, which would be 16, divided by determinant of a. Divided by 16, this is 1. Then y is equal to determinant of ay, which is 48, divided by 16, this is equal to 3. And finally, the value of z, it's equal to minus 64, divided by 16, this is minus 4. So it looks like the solution of this system, using Cramer's rule, is the following. So the unknown vector x, which is equal to x, y, z, this is equal to 1, 3, minus 4. Okay, so this is the solution of this system using the Cramer's rule. Okay, do you have any question?
So this is an alternative to find x.
Yes, but when could this be a good alternative? Can you answer this question?
When A is a square matrix.
That's true. Why?
Because then we couldn't find
The determinant. Yes, you cannot find the determinant for a matrix which is not square. So for square matrices, we can do this, and at the same time, square matrices whose determinant is different from 0. Determinant that will be different from 0 because we would have to divide by 0. Okay. Yes, so it is an alternative way to solve systems of equations that look like this. Any other question? Okay, so if you have no more questions, thank you, Elma. Then, if you have no more questions, I just want to thank. Okay, wait a second. Yes, Christy, you have a question? You can ask your question in written form. I have a question here from someone in the class. How we can prove? Okay, the question is this: how can we prove that two equations define the same plane? How can we prove that two equations define the same plane? Well, now, if you are talking about two planes, wait a second, let me try to understand this one. Two equations define the same plane. Well, first, you look at the normal of the plane. So give me two equations. So if you're talking about planes, so this was the previous exercise. Let's leave this out also.
Professor, I have a similar question to Christy's.
Yes, but let's answer.
How do you extract the normal vector from a given plane equation or vector equation? How do you get that?
Let me ask you on this one. How could we get? What do you think? What is the option? Let's say.
From what we have studied until now, I have one idea, which is the inner product of two vectors. And if you take the inner product of the normal and any vector, you know that its result should be 0 because the angle they make should be 90 degrees.
Okay.
So, but I haven't worked it out. It's just an idea.
Okay, good. We'll come back to your question. So, what is a plane? A plane is defined as a normal vector n times, it's a vector, okay? The inner product with any component x. This is equal to d, okay? Now, if d is equal to 0, this plane is passing through the origin. This is good. But now, let's give a plane P1. Plane P1, this can be defined as, let it be like this, 3x minus y plus 7z, this is equal to 2. This is one plane, okay? Now, let's give another plane. Plane P2, this can be equal to, give me some numbers, any random numbers.
2x
yeah.
plus y
yes.
minus 6z.
This is equal to what?
Equal to 8.
8, okay.
But I have no idea if there's a solution to this.
Okay, so now the question of Christy, I can read it like this. How can we prove that two equations define the same plane? Now, the first thing you do, you check the normal, okay? Two planes to be the same plane, what you need to have is the following. Let these two planes be here. How can they be the same plane? Only if they merge like this, at every point of theirs. If they merge like this, two planes, this is the only way two planes can be the same one. But in order to do this, the normal should be the same. So a vector which is perpendicular to plane 1 should be equal to should be the same direction of the perpendicular vector to plane 2. Okay, so here I have plane 1. What is the normal vector? Is this one. Take this away. Where is the other vector? It's here. So the first expectation is the normal vector has to be the same. These two planes, do they have the same vector? Normal vector? No. The first normal vector for plane P1 is the following. It's 3 minus 1, 7. Okay? The second plane has a normal vector which is 2, 1, minus 6. These two vectors, these two planes are not normal. So for sure they are going to intersect at some point. Okay? So the intersection of these two planes, most probably, is going to be a line. So these two vectors are never the same, and we check it by looking at the normal. Okay? But if you are asked to find what is the solution or what is the points which satisfy these two equations, how would you do that? Christy, did I answer your question?
Professor, can you ask the question again?
Can I answer the question again?
No, can you you made a question. What was the question again with the points? I didn't hear it.
Yes, I asked the following. What is, let's define the problem like this. We randomly generated two planes. Now, two planes, when you have two planes, let's think for a moment. Let's assume we have this plane, 3x minus y plus 7z, this is equal to 2. And then we have another plane, 3x minus y plus 7z, this is equal to 4. Do these two planes intersect?
No.
No, they don't, because they are parallel. They are parallel, and they are going to intersect. They are off by some degree. Okay, so this means that these two planes they don't intersect. They have no common point. They never. If they don't intersect, okay, you can spell it correctly better than me. So these two planes that don't intersect because they have the same normal, but they are passing at different points. They are parallel everywhere, which means that if we have a system of equations, if you have two equations, three unknowns, this system will never have a solution. Okay, so this one geometrically in space, giving the picking up the meaning of how points flow in space, we can say that they don't intersect, or we can say that the system AX is equal to B has no solution. Okay, we did AX is equal to B here in this class, it was the previous week. So AX is equal to B has no solution. What is A? A is the following, is 3 minus 1, 7. 3 minus 1, 7. What is B? B is equal to 4. How would you solve this system? How can you approach the solution of this system? It's always the same. You say 3 minus 1, 7. 3 minus 1, 7. We construct the augmented matrix, right? The augmented matrix is going to look like this. We have two forms. Then, what is the next step? The next step is we do a row operation, which is going to be the following. Row 2 star is equal to row 2 minus row 1. Would you agree here? So then we go next and we say that 3 minus 1, 7, 2. What can somebody from the class help me here? What should I get here?
3 zeros
0, 0, 0.
and minus 2.
No, 2.
No, 2.
Okay, what does this mean? Now, we have done in the previous week that if in the augmented matrix, so this is the augmented matrix, okay? Augmented matrix. If in this augmented matrix you have a row, you have a row para quem tinha leste com escolha de forma e quem indica 0, 0, 0, 0, 0, tu traz me trap, okay, tá bicho? Like tu quem dus. So if you have a row that is full of zeros and you have one non-zero here, what do you say? We say that we have no solution.
It doesn't have a meaning. Let's say 0 is equal to 2 doesn't have.
There is no values x, y, and z such that you would get the 2. Because how do we read this equation? We read this equation like this. These are coefficients, right? So what were these here? Like this was 3 minus 1, 7. This is what it was. Now this 3 minus 1, 7, this becomes 0 times x, okay, plus 0 times y, plus 0 times z, this is equal to 2. Now find me a value of x, y, and z that satisfies this condition. I believe no one can do that, okay? Only Chuck Norris can do that. If you ask him, Chuck Norris will find you an x, y, and z such that 0 times x plus 0 times y plus 0 times z is equal to 2. But probably you don't know Chuck Norris. Who knows Chuck Norris? No one? He's a super.
Everybody knows him.
Huh?
Everybody knows him.
Okay, because he did not confirm for a few seconds. Okay, that's good. So, but other than Chuck Norris and Zlatan Ibrahimovic, nobody can find a solution here, okay? So we say that there is no solution here. Now, this means they don't intersect. But now, these numbers so I believe this part is clear, and at the same time, we also clarified a little more the solution of systems of linear equations. So, be aware, whenever you try to obtain the reduced row echelon form, then you, whenever you see this, you write in the exam sheet, this system has no solution. Now that this is clear, my question that you asked me, what was the question that you asked, Professor? My question would be the following. We have these two planes, and we want to find where these two planes intersect. Which is asking this question, so this question Q1, give me 1 second. The first question that we can ask it as follows. Where do plane P1 and P2 intersect? This is the first question. The second question, or no, sorry, this is equivalent to this. Q2 is the following. Find the solution AX is equal to B, where A is equal to 3 minus 1, 7, 2, 1, minus 6, and B equal to 2, 8. Okay? These two statements, they are equivalent. So finding where P1 and P2 intersect, it's equivalent to asking, find the solution. Because finding the solution of this system, this is forcing us to find X, Y, and Z that satisfy this equation, and simultaneously, X, Y, and Z that satisfy also the second equation. So that's why we construct systems of linear equations. So we have 3 equations, and we're trying to find X, Y, Z that satisfy the first, the second, and the third. Okay, so these two statements are equivalent. Okay, now let's try to solve this one. I think this was clear. I don't want to delete this one right now, but so let me write on the board here. We are good enough. So if the solution of this problem fits here, this means that this is a very simple problem. So let's move ahead. How can we solve this one? We construct the augmented matrix, but before we do this one, let's have a leading one. So let's write it like this: AB is equal to, well, let's do it like 3 minus 1, 7, 2, 1, minus 6, and this is 2, 8. Then we construct a leading one here by doing what? We divide by 3. So we say here, row 1 star, this is equal to row 1 divided by 3. So this becomes the following. This is 1.
Can we subtract let's say the second one from the first one? Or is it wrong?
We can subtract, say it again.
Let's say the second one from the first one.
But then we cannot produce zeros here. We want to have this leading one. Don't forget what we learned in the previous weeks. So I believe, can I continue then? Probably it will become more clear. So here we divide by 3, we get here 1, minus 1 over 3, 7 over 3, and 2 over 3. Then this is 2, 1, minus 6, 8. Now that we have a leading one, what is the objective? It is to produce here a 0. Okay, we want to have a 0 here. How can we make this 0? We can say that row 2 star is equal to row 2 minus 2 row 1, right? And then the first row does not change. Minus 1 over third. This is 7 over 3 and 2 over 3. So then this is 2 minus 2, we get 0. Then we have here 1 minus 1 plus 2 over 3. What does it become? 5 over 3. So this was 1 minus 2 times minus 1 over 3. This is 1 plus 2 over 3. This is 5 over 3. That's correct. And then we have minus 6 minus 2 times 7 over 3. Okay, let's do it here because I can make a mistake. So this is equal to minus 6 minus 14 over 3. And this is equal to minus 18 minus 14. This makes it minus 32 over 3. Minus 32 over 3. Then we have the final answer, with, sorry, numbers. So allow me to erase this one because I believe this is clear. Then we have here 8. Let me do this here. Minus 2 times row 1, minus 2 times 2/3, minus 2 times 2/3. This is equal to 8 minus 4 over 3. This is equal to 32 minus 4, 28 over 3. So we have here 28 over 3. What is the next step? The next step is always... Sorry?
Is it 20 over 3?
I don't know. Let's check. Yes, it's 20 over 3 because this is 24. This is 20 over 3. So, thank you. This is 20 over 3. Now, what is the next step? We try to produce a leading one here, okay? How can we do it? We can say that row 2, we divide by 5 over 3, okay? Then we can move on, on this side, and here we write the matrix again, 1 minus 1 over 3, this is 1. Let's use the board better. Minus 1 over 3. Then we have 7 over 3. And then we have 2 over 3. The first value is 0. 5 over 3 divided by 5 over 3. This is 1. Minus 32 over 3 divided, let's check this one. What is this? Minus 32 over 3. Divided by 5 over 3, we multiply 3 over 5. So we have 32 over 5, 32 over 5. And then we have 20 over 3, 20 over 3 times 3 over 5. This is 4. Okay, we get the 4 here. Okay, then what is the next step? The next step, we look at these numbers. And these are the leading ones, okay? If we have leading ones in a system of linear equations, I have a comment here. Okay, yes, if you have anything to do, the normal time for the class is over. You may go on, and you can watch the recorded material later. So if these are the
Yes, sir. I think it should be minus 32 over 5.
Okay, let's check. Probably, that's true. Okay, that's correct. Yes, this is minus 32 over 5. And then the next step is that we want to produce a 0 here, right? So to do this, we say row 1 star is equal to row 1, and then what? What should we write here?
Plus 1 over 3.
That's correct, row 2. This is what we do, and then let's try this one. This does not change. 0, 1, minus 32 over 5 and 4, and here we get 1. 1 plus, sorry, 1, this one plus third, this is a 0, and then we get row 1, which is 7 over 3 plus 1 over 3 row 2. Row 2 is minus 32 over 5. So here we get, this is 15 times 5, 35, Is this true? Started with 35 minus 32. This makes this 3 over 15, which is 1 over 5. This is correct. Yes, 1 over 5. So this is here 1 over 5. But then here we have 2 over 3. Let's not forget we are in this equation. We have here 2 over 3 plus 1 over 3 times 4. Okay, this is correct. So here we have 3 over, this is 6 over 3, right? This is 6, which is 2. 4, 6, 2. So this is 2, and I hope to make this clear. Okay. So let me take this away. And now, what do we have? So if we have this, we simplified this one as much as we could. We cannot do any better. But now, the next question that we always ask is this. What are the leading elements? What are the leading elements? It is x and y, right? X and y, because this is x, and this is y, and this is z. So leading elements, it is x and y. Which one is non-leading?
Z.
Z. Okay, so we just followed the procedure. Okay, so it's not a difficult task. Solving a couple of examples, you can always bring back you can always remember everything. So if z is a non-leading, then we can assign z equal to s. So we can, this is a free variable. What is s? S is any real number, any number from minus infinity to plus infinity, including the 0. Then we come back here and we write down, what is x? Or what can we read from the first equation? Can somebody read the first equation for me?
X
Yes?
plus 1 over 5 times z
Yes?
equals to 2.
That's true. And what is the second equation?
Y
Yes?
minus 32 over 5 times z equals 4.
Is equal to 4. Okay, that's correct. What is z then?
Is equal to s.
Is equal to s. Now, allow me to substitute here s. Because z is equal to s. It's a free variable, okay? So it's good to write those every solution in terms of s. So let's carefully reread this. And since I need this space, allow me to erase this one for a second. And then we can rewrite the following. X is equal to 2 minus 1 over 5s. Y is equal to 4 plus 32 over 5s. And z is equal to s. So here, so then what is the next step? The next step is the following. X, y, and z. This is equal to what? We have some constant values plus s times some.
I think we have 2, 4, 0.
Sorry, say it again.
2, 4, no, it's at the y component.
Is it good?
Yeah, I mean there, yes.
32 over 5. What is 32 over 5? This is 6.4, right? And then we have 0, 1. So this is the solution of the system. So we started with 2 randomly assigned planes. So we started with these 2 planes. And the question was, where do they intersect? Or we can say, find the solution of this system. So this is how we defined it. And finally, we found it. So it looks like the x as a vector, as an unknown vector, this is equal to a constant vector p plus any value s times v. Okay, where v is this vector or this orientation. So we found, and this is the equation of a line. We know this, right? Okay, so is it a little more clearer? Do we have any more questions? So
Professor,
Professor,
can I ask?
Yes.
If we have a parametric equation of the plane, is it possible to derive from that equation the Cartesian one?
Yes. Yes.
What method is used?
Give me some numbers and let's find it. So this part here, or we're not losing much information. Okay. So you said that if we have the equation of the plane, right? What is the equation of the plane? The equation of the
If we
plane.
have a parametric one,
Yes. So let's do it.
it
Like
will be the position vector p
yes. So let's
plus
P plus SV.
sv plus t w.
This is the plane. Then just give me some numbers.
2, 3, 0.
Yes.
-1, 2, 3,
Yes.
and 4, 5, 2.
Okay, that's good. So this is the equation of the plane, and we want to find this one, the Cartesian representation. Then to do this one, so all you need to do here, you just need to remove s and t. How do you do it? You express s as a function of the other variables, and you substitute. This is the technique. That's it, okay? Which means that it's not that we need to do, we can solve this one step by step, but your only trick is that take away, remove s and t, which are numbers that go from -infinity to +infinity, or they are numbers including the zero. So there are subsets in the R space. So then let's read the x. X is equal to 2 minus s plus 4t. Okay, this is the first equation. And then this is easy. When you go to the second year, when you're going to do electromagnetic field theory, you're going to really have much more fun than nowadays. So from the first equation, what can we learn from here? We get here that s is equal to 2 plus 4t minus x, right? Would you agree here?
Yes.
Okay. What is the second equation? We write that y is equal to 3 plus 2s plus 5t. So let's substitute the s here. So this is the traditional equation. So we do it step by step. Then we say that y is equal to 3 plus 2 times s. What is s? Is 2 plus 4t minus x. Okay, this is the s. Plus 5t. Then we can move a little further. We can say that y is equal to 3 plus 4 plus 8t minus 2x plus 5t. Right? It's simple, we just follow the procedure. We can simplify it a little further. We have here 3 plus 4, this is 7. T, what is next? Okay, then the next step is the following. We can, so, ehojim sănăr. Pot tănsi do agent tănë. Shiko ka goxha intuit, pra. Së me hoqëm, tani skema së, ku të që ke së shku me këtë. Now you have to write t, as a function of x and y. Okay? Pra nga kjo equacioni do gjesh sa është t-ja. Është I qartë? Okay, let's do the numbers. So here, what is t? Let's write it like this. To keep it simple, let's write the following. Let's write 13t is equal to y plus 2x minus 7. Okay? So the two fundamental equations that we need, so what did we say? Remove s and t, which means that we have this is the first important equation, and this is the second one. Okay, then we move a little more. We write the third equation. What is the third equation? This is z is equal to 3s plus 2t. So the equation of the plane that was given above is equal to this, and then we substitute everything at z. So let's use some more space. This is z is equal to 3 times s. S it's equal to, wait a second, so this is 3s plus 2t. I'm trying to figure out a relatively easy way. So 3s, we write this one, 2 plus 4t, 2 plus 4t minus x. Okay, we did the first part, plus 2t. Plus 2t. What is t? T is equal to 1 over 13 of y plus 2x minus 7. Okay, so do your third, we divide the 2 by 13, y plus 2x minus 7, and then this is equal to, this is, we are going to substitute t once more here, okay? So once we substitute this t here, then the whole expression will be only a function of x, y, and z. So let's do this one. This is 6 plus 12t. But I believe you see this 12t here, right? You multiply. So let's substitute the t right away. So what is this t here? T is 1 over 13, so divided by 13, times y plus 2x minus 7. So this is our 12t. Are we good?
Yes.
Okay, minus 3x, and then we continue again, plus 2y over 13, plus 4x over 13, minus 14 over 13, okay? So this is the solution. This is the solution. Since we understood this part, we can erase this one and we can try to simplify it a little further. So since we selected these numbers randomly, getting some ratios or rational numbers, it could have been expected. But then we can simplify this a little further. We say that z is equal to, let's pick up just the numbers, the constant numbers. We have 6 minus 7 times 12 over 13. We have 6 minus 7 times 12 over 13. So we took this out, minus 14 over 13, minus 14 over 13. So this is also written. Then we have to include the y. Then we have here plus 12 over 13y. Okay, with this the next y is here, is 2 over 13y. Then we are left only with the x's. So this is 24 over 13x plus 24 over 13x. So we wrote this, and we have minus 3x plus 4x over 13. Now, this 24x over 13 and 4x over 13, we can write this one 28x, okay? Не запускали, sorry, Mr. Carter, ale Carter instead. 28x over 14 minus 3x. Where's your minus 3x? Now we wrote everything, okay? Then z is equal to, let's put together so for x, what do we have for x? For x we have 28 minus 39 over 13. This is equal to minus 11 over 13x. Okay, x is gone. Then for y, we have plus 14 over 13y. And then we have the constant terms here, which will be plus, we have 13 here, and then we move like this. 13 times 6 is equal to 78 minus 84. What is this? 12 minus 84 minus 14. So if this is the case, this is 98 minus 78. This is 20 plus 20 over 13. So this is the plane, equation of the plane in Cartesian coordinate representation. So this plane here and this plane here, they are the same. Okay? This is the parametric representation, and this is the Cartesian representation. Is it clear?
Yes, it's clear.
So, Professor,
Yes.
for two equations to represent the same plane, they need to have same normal ones?
Well, for two equations to represent the same plane, everything should be equal. Okay.
Everything should be equal.
Yeah, I mean, I started by generalizing the problem by discussing the normal component, but for two equations to represent the same plane, we have here 3x minus 2y plus z. This is equal to 2. And the next plane is 3x minus 2y plus z. This is equal to 2.
Okay.
Yep. Mm-hmm. Or did we spend the whole time for nothing just to understand this one, right? I could have said this right away.
No.
Okay, very good. Any more questions? No? Okay, so if you have no more questions, I think we can end this session. But I'm available if you have any